Okay, today we have Gibney who will tell us about the reduction of the.
Thank you. Wow. Thanks so much for inviting me to give a talk here. I'm really excited to tell you about this work. So I'm going to talk to you about an old problem. Some of you know this problem pretty well, and I'm not sure, maybe some people have never heard of it. It's an old problem about the closed cone of curves on the moduli space of curves. And I looked up to see how old it was. It was initially mentioned by Sean Keel and James McKernan in a paper in 1996, just about MG. They mentioned it as a question. So it goes way back. It was only mentioned as a conjecture in 2003 until it was stated. So this is the F-conjecture, and there are a number of different ways to state it. So it says that, for example, every curve on the MGN bar is numerically equivalent to an effective sum of a special class of curves, which I'll define, so-called F curves. And you could have Q coefficients. And so what are the F curves? This is the right board, right? Okay. So definition, an F curve on MGN bar is is any numerical equivalence class, and I could describe it in a couple of ways of the one-dimensional boundary strata. I'm going to do lots of examples, or we could restate this as numerical equivalence classes of images of certain clustering maps, which I'll show you. From the one-dimensional moduli spaces, M11 bar and M04 bar. Okay, and I'm going to give some examples shortly, but I want to just point out some properties of the F curves for a moment. So properties that are interesting for me, properties. First, there are only finitely many of these. Another thing that's interesting, something that was observed by blankers, Vance blankers. So let me just say here, this is really a problem about the closed cone of curves. That the closed cone of curves is equal to the cone that's generated by these special curves. And Vance blankers proved that in genus 0, I'll say it and then I'll write it, every F curve spans an extremal ray of the cone of the closed cone of curves generated by F curves. So in other words, you can't, in genus 0, you can't write any F curve, a single F curve, as a sum of other F curves in genus 0. So they're really, there are no relations between single F curves as a sum of other F curves. So in genus 0, every F curve spans an extremal ray of the cone of the closed cone of F curves. I know I haven't really defined that, but just, I think you understand what I mean. And then the same thing is true in genus one. This was proved by my student, Dae-Bum Choi. But in genus bigger than or equal to 2, this is no longer true. So Dae-Bum showed that. So once you go higher than genus 2, then you start having relations between single F curves. I think that's interesting. So I'm going to give, so what am I going to do today? Let me just tell you. I'm going to give some examples. Just in a moment of F curves. And I'm going to restate this problem in terms of divisors. I'm going to tell you what we know about the conjecture. I'll say what we know. And then I'm going to show you a new result, which is a reduction. I'll explain I'll give a reduction. And this reduction would give the conjecture for all genus. Let me just say it and then I'll write a few words. It would give the conjecture for all genus and all marked points if you knew enough in genus 1. So what would be enough? And I'm going to explain all of this. Enough means if you could show that any F divisor, so I'm going to define all of these things, a divisor that non-negatively intersects all of these curves on M1n, that intersects just a small number, relatively small number of particular type of F curves. If you could show that those curves, those divisors are nef, then you could have the conjecture. Okay, so I need to explain why that's true. But so I'm gonna, it gives the conjecture if you know enough about the case M1n. Okay, so we have to build up the terminology before I can state that reduction, but I just wanted you to know where we're going. Okay, so, yeah. All right, so.
Can I ask a quick question on
Yes.
this? No?
Great.
If I look at things like MG and bar, and look at the effective cone of curves, is it known that it's closed?
Well, you're supposed to take the closed cone of effective curves.
But-
You take the closure of the cone of effective
In
curves.
general,
In general.
but the F-conjecture would, in particular, say that it's not necessary to take the closure,
Well, that's correct. Yeah.
but it's that
Yeah.
weaker consequence is, I suppose, not known.
Yeah. Now, let me just say right away that I don't believe the conjecture is true. So, let me just say that I'm going to explain. I can't, I want to restate the conjecture in terms of divisors, and then I want to say what cases are known, and there are quite a few cases that are known. But the conjecture is not supported by the cone theorem. So the cone theorem, this conjecture, because of this first fact that there are finitely many F curves, that says that if you look at the cone of curves, it should be, the convex hull of finitely many extremal rays, right? So the cone theorem of Mori says that if you look at the half of that cone that is K negative, that intersects the canonical divisor negatively, that should be true about that part. But almost all of these F curves are K positive. And moreover, Mori's theorem says that there should be accumulation at that hyperplane. So the cone theorem does not support this conjecture. That's one thing. Another thing is, well, it's 20 years old, and a lot of people have worked on this problem. So I think that there's a good chance that it's not true. And what I like about my reduction is that it isolates some divisors. It tells you, which I'll try to point this out, is that it tells you some limitations of what we know. So I don't think my divisor or my reduction can prove the F-conjecture. I think what it can do is it can say, if you're looking for a counterexample, then look for this, start on M1N and take an F divisor that has these properties and look for your counterexample there. So anyway, that's a little warning. So it's a fun conjecture. A lot of cases are known, and I'll tell you what those are. But I'm not really one of those people anymore. I used to think it was true, and now I'm thinking it's not true. Okay, so let me go. Let me show you what some F curves are. I hope that doesn't make it not fun to listen to this talk, because I think mathematicians like to solve a problem but maybe the problem is to find a counterexample. Okay, so let me show you some examples of F curves. Okay, so the second way to define them, they're images of these clutching maps. So there's exactly one kind that's an image of a map from M1. I'm going to call it En. So you take a curve of genus 1 with one marked point. And how can you get a curve of genus G with n marked points? Well, you can attach a point. So I'm going to attach a point X. What is it? It's a curve, and it has some marked points on it and an attaching point. And this is really just a point in M G minus 1, n plus 1. X is just a point. This is X. And now I'm going to attach alpha to P. And so what I have here is my marked points, P1 through Pn. I started with a curve of genus 1, I have a curve of genus G minus 1, and so altogether I have a curve of genus G. G with unmarked points. You can do a lot more with M04. There's tons of things you can do. So we're going to get a bunch of different curves, F curves sitting inside of MGN. And let's just start maybe on M0N. Let's start with, there's M0N is the simplest thing. So these come from taking a partition, I union J union K union L equal N. And what we're going to do is attach genus 0 curves where we put marked points indexed by those partitions. And actually, for our purposes, we're going to be working with n plus 1. So what I really want to do is fix one of them. I'm going to call it L prime that has this extra n plus 1 point. And I'm going to call this curve C, I, J, K, and then I'll put down here the rest. So really I have I union J, well, let's just do it like this. And this is just the complement. And I'm just remembering that on the bottom, I put the n plus first. And it's useful to keep track of it like that, because we're going to use a certain basis for the card group where we emphasize the n plus 1, n plus first point. So that's what it's useful to denote the curve like that. So this is really all you have for genus 0. Let's look at genus 1. We have more. So I like to give them silly names because it helps me remember. So we have this kind. This is not a big surprise. The only thing different here. So we're going to go to the same kind of thing. So we're going to M1N. I'll label it after I say what happens. The only difference is we're going to genus 1. So one of the components has genus 1, the other ones have genus 0. But again, I have to partition the marked points. So I put them here. And I can put the rest here. L is just the complement. Now, here well, I mean, I'm just gonna write I, J, K, and L. And in fact, you can see that through this, there's a natural map from M0, N+1 to M1N. This is, I'll call this, there are a lot of F's flying around here. It's the flag map. Usually it's, you can define this in general. So I have my first N marked points and my N plus first. And I can just attach a genus 1 curve. So if I were to push forward one of the F curves here, push forward this one. Say I have I, J, K, and here I have my L union N+1. So on this leg, I have my N+1. I just get, put my genus 1 at the N plus first point, and I just have this F curve. Okay, so these are related. These curves are related. Okay, but in genus 1, you have more. So we saw that we have F curves from partitions of the mark point into 3 or 4 sets, but there are more partitions into 3 sets and into 2 sets. Let's do the simplest ones. So if I have any partition into 2 sets, I have an F curve. So this I'm going to call A, B, empty set, and you'll see why in a minute. I call this a beloved only child. We'll see why, BOC. And here, we could also, so actually a partition into, if I have, let me show you that I get 3 different curves. If I have a partition into 3 sets. So there are 3 things I could do here. I could put I, J, and K here, I, J, and K here, or I, J, and K here. Okay, this is actually the same thing where K is empty. So this is Cij, K, this is the genus 1 part. Cij, this is the genus 1 part. Cjki. So from this partition of the marked points into 3 sets, we get a triple of curves. I call these triplets. So these are, I'll refer to these as triplets, sibling triplets. They're related. Of course, you could have triplets that are from different partitions and they wouldn't be siblings. And I'm giving them these silly names because it makes it easier to state the theorem later. Okay, so this is it. For genus 0, we don't have this first curve, this, we don't have this because we couldn't have attached a genus 1. Okay, in genus 0, we only have this kind of a curve. In genus 1, we have this one, we have the ones that are related to the genus 0, and then we have these triplets. Okay, And if you keep going, different genus, you get more F curves. You just keep getting more and more.
We will not go there today.
Yes. We only care about genus 1 and genus 0 today. Okay, so now I want to state the problem in terms of divisors. So let me just tell you what a nef divisor is. A divisor D on a projective variety is nef. Say X is nef if D dot C is greater than or equal to 0 for all curves C on that. All curves C on X. Okay, and so an example, there are lots of examples of nef divisors. For example, if you have any morphism from your projective variety to another projective variety, and if A is ample on Y, then the pole back of A, this ample divisor is nef. You can see that by intersecting with the curve. Those are just points, we could push them forward. And by the projection formula, this is the same thing as the ample divisor intersected with the push forward of that curve. And the push forward of a curve can either be points or it can be a curve. If it's points, this is 0 if F contracts the curve. And otherwise it's positive. If it pushes forward to a curve, then the ample divisor intersects positively. So this is always greater than or equal to 0. So pullbacks of ample divisors give you natural examples of nef divisors. And now you can add two nef divisors, you get a nef divisor, take multiples, positive multiples of a nef divisor, you get a nef divisor. The set of nef divisors forms a cone. And I'm going to call that cone nef X. And that cone, it's a theorem that it lives in the closed cone of effective divisors on X. And if you know basic information about nef divisors, you can say something about the variety. So here's an example to illustrate that. On MG, so the interior of this cone is a cone of big divisors. Those are divisors that are of the form ample plus effective. On MG, every nef divisor is big. So in other words, on MG, except for at the origins of these cones, the nef cone doesn't touch the sides of the closed cone. In fact, it's interior to the effective cone. So what that means about morphisms is that there are no non-trivial vibrations. Any non-trivial morphism on MG is birational. There are no non-trivial maps from MG bar to any lower dimensional projective variety. Other than a point, that would be trivial. Okay, so no non-trivial vibrations. So I'm telling you this to tell you why nef divisors can be useful for studying a variety. Okay, there's a similar result about MGN if G is bigger than or equal to 2. It says that all non-trivial vibrations of MGN for G bigger than or equal to 2 are a composition of point dropping maps followed by a birational map. In genus 1, there are some different kinds of vibrations, but they're not all classified. Okay. Oh yeah, I see what you mean. It is a little sticky. That board. Okay, now the F, I'm trying to restate this conjecture. So we say a divisor on MGN bar is F-nef. We'll say a divisor D if D dot C is greater than or equal to 0 for all F curves C. Okay, so you can similarly define the F-nef cone. And the F-nef cone, if you think about it, of course, if you have a nef divisor, then it's going to have the property that it non-negatively intersects all F curves. So the nef cone will be contained inside. And let's do this, MGN, the F cone. And the F-conjecture says that these two cones are the same. It says that the nef cone is actually contains this F cone. So to remind myself what notation we use for that. Okay, so let me just say what cases it's known for. So let me take the two extremes. So for n, so like say for let's take n equals 0. So results. So we're talking about MG. The conjecture holds for G less than or equal to 35. And the best latest results are by Maxime Fedorchak, who recently, or maybe it's not recent, I don't know. But anyway, he got the last 10 cases. Oops, 35. And now for G equals 0. So for N0 N less than or equal to 7, that record is held by Keel and McKernan. So n equals 8 is still up for grabs as far as I'm aware of. There's also some intermediate results for various SG invariant. You know, you could ask for SG invariant F divisors on MGN. And the reason that that's relevant is that they're related to, let me do this on M0 G plus N. And the reason that's relevant is that these, there's a theorem, and this is due to GKM, myself, Keel, and Morrison. This is pretty old, that says that if the conjecture holds on for these divisors for SG invariant, I'm simplifying this, F divisors on M0 G plus N, then it holds on MGN. And in particular, so this is pretty well known. Less well known is also from the same paper, the F-conjecture on M0 N plus 1 is equivalent to the F-conjecture on MGN, on M1N. Okay, so if you could prove the F-conjecture on M1N, then it would be true on M0 N plus 1. And then it would be true, of course, for, you know, invariant guys, and it would prove it for all genus and all that. So now these are really different kinds of problems. I just want to give you some examples, like, you know, just for say the Keel-McKernan case, like if we're looking at this F-nef cone, let's say 0n, this is the cases, the Keel-McKernan cases. The card number, the dimension of the vector space where the cone lives, of M0n. I want to compare this and the number of extremal rays of the cone. Extremal rays. I want to just compare this really briefly to the same problem for the SG invariant. Like if we look at the F-nef cone for MG, and we look at the so in other words, we can look at M0 G mod SG. These are actually equivalent, and the Picard number, where the space, the dimension of the space where it lives, and the number of external rays. I just want you to see how different these problems are. So in this case, just a couple of examples so we can see. So the Picard number here is the greatest integer less than or equal to G over 2. So that's small. For a while, I can just write these down. So like 6, 7, 8, 9, 10, you know, we can go all the way down to 12. And I can illustrate this. The number of extremal rays is very small. So Picard number, you know, you can do the thing by yourself. 5, 5, 6. So these are really small vector spaces where they let these things live. We have 2 extremal rays for 6 and 7. Then we have 4, then we have 7, then we have 10. So in this, you know, MG case, this is really a doable problem for low G. Over here, let's just do just a few cases. So for n equals 5, Picard number is 5, 10 external rays, not a big deal. N equals 6, Picard number 16, 3,190 external rays. N equals 7, Picard number 42. We've never been able to calculate the number of external rays. We've tried, and we've killed at least 2 computers. So it's just a big problem to do with a computer. I mean, I like to point this out because it seems like, well, why can't you just have a computer check? It's just a lot to check. Okay. All right, so this is.
How does the Picard number of M0 plus 1 bar and M1 bar?
That's a really good question. So let's compare them. And that'll be useful information for later. So the Picard number of M1n is 2 to the n minus n, and the Picard number of M0 n plus 1 is 2 to the n minus n plus 1 choose 2 minus 1. So when we take the difference, 2 to the n minus n plus 1 choose 2 minus 1, we get n plus 1 choose 2 minus n plus 1. And this is n choose 2 plus 1. And that is very important information. Okay, so I think, okay, I'm gonna maybe put this up again. Okay. So I just want to say a tiny bit more about this less well-known equivalence of F-conjectures, because I want to use it. And then I'm going to state a proposition. So maybe I'll put it over here so we can keep it up. Since I don't think I'm going to be moving this board up and down very much. So we have to remember this map from M0 n plus 1 to M1n. And the map just takes the genus 0 curve with n points here and this plus 1 point. And it attaches a genus 1 curve. And the conjecture, this theorem from GKM 0.7 says that I'll say it here, say it out loud for a minute. Every F divisor here is the pullback of an F divisor here. And the F conjecture here is equivalent to the F conjecture here, okay? A divisor here, in other words, I mean, another way to say this, an F divisor here is nef, if and only if its pullback is nef here. So and that's what we're going to use. A divisor, an F divisor on N1N is nef if and only if, we're only going to use if, but I'll just say what I'm going to use. The pullback is nef on M0 n+1. The pullback is an F divisor and we want it to be nef. Okay, that's what's going to be used. Okay, so here's the proposition. This is not the main reduction. This is used in the reduction. So I'm going to call this proposition star. Okay, so suppose the F conjecture, give myself password, holds on M1N -1, and D is in the F-nef cone of M1N. Okay, so we have an F divisor on M1N, and we know the conjecture holds for, M1K, K less than or equal to N-1. Then, so D is nef if D contracts any of the following curves. So when I say contracts, I just mean it can, when you intersect it with any of the following curves, you get 0. So there are 3 conditions here. The first condition is that if it contracts a beloved only child, is the first condition. So if it contracts any of these curves, for some 2 partition, or if it contracts any pair of sibling triplets. So just to remind you what those are, we have these 3 curves, which look like different ways of labeling with a partition ijk equals n. For some 3 partition, so these are okay. And the third condition is a list of, so I think of this, we only get 1 curve from this partition of n into 2 sets. We get these related curves with a partition into 3, and then we get a bunch of unrelated curves potentially from different partitions. So the third condition is a list of different ways of taking cousins, different triplets from different partitions. And if you contract them, then the divisor is nef. So let me list some of them. I call these cousins. So A, IJK, this looks complicated, but I'm telling you because I want you to get the sense that there are a lot of conditions. Okay, so GK union GKL, for some part, I union J union K equals N, and one of a choice of L in I or J. And now these are sets of curves. This set GK are curves of the form where we take just singletons. And this set of curves look like the following. Where here K prime is a subset of the points in K, L prime in L, and the only restriction is that when we take the union of K and L, K prime and L prime, we get something proper in K union L. Okay, so I'll do some examples to show. Maybe it's a good idea to do. These are really diverse in nature. Like you can get a bunch of different ones. So for example, if K is just a single set, there's just, say, the simplest one actually is when K and L are have just one element to them. So if we start with a curve that looks like, if our J and K are just a single point, then, sorry, change my notation all the time. GK is empty and GKJ is empty. So just D intersecting that single curve will give a nefness result, okay? And for example, if we could just take K to be a singleton and J to be 2 points, then still GK is empty, but now GKJ has 2 more curves. So altogether, we have 3 curves. And then if you do the opposite, if you take K has 2 points and J has 1 point, you get 4 curves. And then the larger K is, the longer your set of conditions becomes. So this is a really diverse set of conditions here. Oops. Yeah.
What are the principles? Like,
I'm going to explain that. I'm going to explain the principle behind it. Yeah.
okay.
Yeah,
another-
I will explain the principle. That's why, I mean, I was happy to have the opportunity to give a 2-hour talk so I could say how to prove this.
So
yeah.
what is pair of sibling?
It means any 2 out of these 3
Okay.
curves. Yeah, any pair. Yeah, so I call them sibling triplets because 1 3 partition defines 3 curves. And and I'll explain exactly why. If D contracts any 2 of them, doesn't matter which 2, then D is not. And it actually follows from a curve identity. So I said in genus 0 and 1, there's no single curve that there's no identity that takes a single curve and writes it as a sum of other F curves. But you can take a sum of 2 curves and see that it's a sum of other curves. And in this case, a sum of any 2 of these curves involves a beloved only child and another curve, one of the kind that has that's in common with M0 and +1. And then, so if you contract 2 of these, then you contract 1 of these and another one. What that says about the nef cone is that these faces of the nef cone are touching. So that's one of the principles to answer one of your questions. The proof that this defines nef divisors is totally different, but we get this through a curve identity. And I break them into 3 pieces because the proof that these part 3 are nef is really slightly different than either one. Like you run into each of these cones in different ways, each of these different faces in different ways.
But things inside GK are cousin to each other, or G?
No, not necessarily. I mean,
What's
they're-
a cousin?
cousins just mean they're triplets, but they're not siblings. So that's what I mean by cousins. These are all triplets. All of these are triplets, but they're not sibling triplets in general. If you have few enough March points, then you'll see for some of these conditions that you get sibling triplets. There. So there are overlaps in these conditions if your numbers are small enough. But generally speaking, like for example, if we only had 4 points, I'll do some examples later where you see that.
Then D has to contract all of them in the list.
Yes, so in this case, if K is empty, if K just has a single point and J has a single point, it's just a condition on one, you know, it just has to contract one curve. And like, that's what that's what I'm saying here. If we're just, if our initial condition is this, that's it, that's all we need. But if actually J was, you know, 2 points, then we need actually 3 curves. If K had 2 points, then we need 4 curves. So, you know, your initial conditions determine how many curves you need. So it becomes, you know, there's a similarly, so this is a pain to write down. There's a similarly annoying one to write down. And then the other 2 are pretty nice to write down. I don't know if you want to see the other annoying one. I'll show you. Why not? Just to give you an idea of the, so I'm just going to write it very quickly. There, we start with 3 curves. I, L, K, J, K, L, and then we take G, I, and one of, this is my least favorite condition, but it is useful for checking the n equals 6 case.
So here the decapitalized letters mean single points, right? Or are these?
Yes,
sets again?
that's right, single points. When I do that, so I could do this, when I, exactly, thank you. Right, and so here I is the complement of I, J, K, and L, and this is for some I, J, K, and L, and so there are 2 more conditions that are easier to write down. Then I'll make a definition, then I'll tell you the reduction. So these first 2, you know, depending on, I mean, okay. So here is C, I, J, K, where, so this is just the complement. When I don't label it, it just means the complement. This is J different than I. Oh wait, so that's the last one, sorry. J and J, union, one more curve. So I'm gonna call this K. I, K, and then the rest. And this is for some I and N. And a subset J and I complement. So if we took just J to have one element here, these would be sibling triplet, or these would be sibling triplets. So so if this set had just one element in it, then over here we would have, you know, we would just be switching which ones we use. But for bigger than that, they're not sibling triplets. And the last condition, so we just take everything else such that J is different than I, and here is for any index I. So I'll show you how to prove this one in the second part of the talk. So anyway, what should you take away from this? There's a bunch of conditions that, you know, allow you, you know, if your divisor, you know, contracts these curves, then you can just use this result to show that D is nef. And I'll explain how that works in part 2 of the talk. But now I want to state what the reduction is. Okay. So in order to do that, I want to make a definition. And the definition is a set of curves is said to be related. And we'll say a set S of curves is said to be related if D dot C equals 0 for all C and S implies that D is nef by proposition star. Okay, that's why I was calling them sibling triplets and cousins. All of those curves are related. Because if D contracts those curves, then D is nef. And I'm doing that for the convenience of the following result. And I call it a theorem, but it's really an observation. And here is the reduction. So the F-conjecture on M1N follows from the F-conjecture on M1 N minus 1 if any F divisor that contracts N choose 2 independent, unrelated triplets is nef. And June just proved the theorem already, so I can go over it. I guess the value of it is this proposition, but let me just sketch a proof and then we'll take our break and go to part 2.
You mentioned briefly that the proposition that was erased just now is useful in checking the case n equals 6.
I've checked it with n equals 6.
How is knowing this helping?
Well, let me do a simple example with M05. Okay, so M05, that corresponds to M14. Okay, let's just assume the theorem first. The reason I'm not doing M06 in front of you is that there are just millions of cases, as you know, with the extremal rays, 3,109. Okay, so let me shut this on, turn off the volume. Okay, so let's just think about, and we can do an example that, well, okay, let's assume the theorem. So the theorem says that if we know if D is in the F-nef cone of M14, and if it contracts 4 choose 2 equals 6, unrelated triplets, so if we know that D is nef whenever it contracts this many unrelated triplets, then the F conjecture holds. Then F-nef of M14 is equal to the nefness. Okay, in other words, the F conjecture on M14 is true, and so this is already known to be true, but this would give a different proof. Okay, so we have to think about how many triplets do we have. So we can just count them up. So we only have 4 points. So what are our options? Well, we can have curves like, so let's just write them down. So we could have something like this. So this is a partition, you know, of size 1 plus 1 plus 2, right? And it, so say we have, you know, I union J union K equals 4, and, you know, I has 1 element, J has 1 element, K has 2 elements. So like I, J, and here's my K. And so here are the 3 different curves that we could have. Sorry. Here are 2, okay. Okay, so we know that if you intersect either of these, then you're not, right, by one of the conditions. So the only possibility left is to take, you know, our 4 choose 2 curves from here, right? But then we've got too many, because we know from that last condition that, you know, if we intersect all of these in degree 0, then we're nef, because, for example, we have 1, 2, 1, 3, 1, 4, and that's enough, right? 3. So you just don't have, you know, enough curves to produce the number of, you know, you're done. There's nothing to check. So for n equals 6, it's a lot more complicated. But you can check all the cases and you can see that you're okay. You've got everything. So that's a really combinatorially different problem. I mean, remember how this number of extremal arrays went from M05 to M06, and the problems are equivalent, so it's hard.
So a triplet's a single curve? Like a triplet is 1 element of.
A triplet is 1, and you could have related triplets, sibling triplets. They're given by the same partition, or you could have triplets from different partitions. Those are potentially unrelated. If you have a collection of potentially unrelated triplets that cause a divisor to be nef, then they're related, they're cousins. Does that make sense? Okay. So I did not check beyond n equals 6. I would like to check for n equals 8, and it's a really hard graph theory problem, just to get all the cases written down.
Wait, is it possible to check for n equals 7?
Yeah, I think it would be possible. I mean, but it's a hard graph theory problem. And the reason I accepted your invitation to come here, and I'm coming here for a week, is I'm going to try to check. I'm just going to not talk to anybody and try to check all the cases. But I don't know. I don't know if I can do it. I mean, I'm not a graph theorist, and it's really hard. There are a lot of cases to check.
You've been here when DeepMind was here last week to test.
It's just not something I think that, I mean, maybe you can get a computer to do it. I definitely think that it's useful to have, I found it useful to have some help with a computer to find all the cases. Yeah. But then you have to kind of, there's some like thinking to do, like which of the conditions to use and so forth. If you just let the computer go, I don't know that it's really useful. Okay, so can we just do a quick proof of this, or should I wait till after the break?
It's up to you.
Okay, well, let's just do this real quick and then we can focus on the proposition after the break. So I just want to explain like why this is the observation that makes this true. And so what is the observation? Well, remember, just put into context, there are a finite number of extremal rays of this cone. And so if we can prove that this result holds for the extremal rays of the cone, then it will hold for any of the divisors, okay? So what does it mean for a divisor, an F divisor, to span an extremal ray of the cone of the F cone, okay? What has to be true? So this cone lives in a vector space of dimension equal to the Picard number. It's 2 to the n minus n dimensional vector space. So if D spans an extremal ray, of the F-nef cone of M1n, then D must contract. Let's call this rho minus 1, independent, this is important, of curves. So we're going to start with that assumption, okay? And now we know that, moreover, D is nef if the pullback of D is nef. Now there's one easy way for that pullback to be nef, and that is if you pull it back and it's trivial. And it can be trivial very easily if it intersects too many of the curves that are pushed forward. If it intersects too many curves like this, you know, N1, N2, N3, N4. If the pullback of D fills too many of these curves, then when you pull it back, it will just be trivial, and a trivial divisor is nef, trivial and nef. So you have to keep it from intersecting. You have, without loss of generality, we can assume it doesn't do that, okay? So how many is too many? Too many is rho of M0, n plus 1, which is 2 to the n minus n plus 1, here's 2, minus 1. So it can intersect at most this many minus 1. So we can assume that D contracts at most that many. So at least the difference, you know, rho of M1n minus 1 minus rho of M0 n plus 1 minus 1, which we know is the difference between those Picard numbers, and we already did that calculation, n plus 1 of the other type of F curves. There are two other types. There's the one that comes from the elliptic, you know, attaching a genus 1. So we may have one like that. And the other ones have all to be triplets. So any divisor that spans an extremal ray of the cone has to contract and choose 2 triplets. Now, if there are any of the triplets that we listed in that annoying proposition, then D is nef. So we can rule those out. So what that leaves us with is that we need to check that a divisor, an F divisor that contracts and choose 2 independent. That's important because every time you contract a curve, you contract a bunch of curves. You get a bunch of dependencies. Independent, unrelated triplets is nef. Okay, so in part 2, thank you very much. In part 2 of my talk, I want to focus on the answering your question, which is like, what is the idea behind the proposition? And you know, for anyone who's got the stamina to, or whatever, nothing else better to do. So I'll talk to you later then. 5-minute break. Thank you. Okay, so shall I start? Should I look back at that guy? Is it okay to start? Okay, thank you for coming back. I appreciate it. So I want to focus on the idea of the proof of proposition star. So what are the methods to prove it? Of proof of proposition star, and I'll check not all the cases, but some of them. And then I want to say, what does the proof say about the nef cone? And what are the limitations? With F-nef, what part of the cone does the proof see, in my opinion, and where should we go? Where to go? So in order to get started, I want to say a little bit about, I have to say a little bit about about divisors and, well, divisors on M1n and M0n plus 1. So let me say tell you about a basis for each of them. So on M1n, the rational Picard group is generated by the boundary classes. We have actually a basis given by M1n, given by halfway here. Delta irreducible, and the set of boundary classes delta 0s, such that S is in the marked points and S has at least 2 elements. And of course, we can write lambda and the psi classes in terms of those, just if you're wondering. So this is lambda is 1/12 delta irreducible, and the psi are the sum of the delta 0I. Just to justify, the formula is all right for F divisors. Just following the notation in GKM, I write the divisor minus B irreducible, delta irreducible, minus the sum of B0s, delta 0s. And then we can write down what it means to be an F divisor.
What is delta irreducible?
Delta irreducible is the class of the boundary divisor delta irreducible, where delta irreducible is the closure of the locus. Some people call it delta 0 of curves with a single, generically single non-separating node. So, yeah. And here, of course, we have marked points. Okay, so a divisor D on M1n is an F divisor. If it non-negatively intersects the curves that we talked about before. And the intersections are -12 B irreducible plus B0n greater than or equal to 0. The second one, I can put the I can intersect with a triplet or a beloved only child. I get the same formula. Let me just write it. This is a triplet. This is a triplet. Unless K is empty, in which case we would have IJ. So if I union J is N, it's something very important. Okay, so this intersection is B0I plus B0J minus B0I union J is greater than or equal to 0. And this is the same number, only the I union J here would be all of N. So these are actually, if you look in the paper, GKM. These are really the same type of curve. They're type 5 curves. And the third condition so I find it easier to fill these. Let me do it in the opposite order. Say we have N1, N2, N3, and on the genus 1 curve, that's just the complement. N1 union, N2 union, N3. This can be empty because it's a genus 1 curve. And the intersection here is B0, N1 union, N2, union N3, plus B0, N1, B0, N2, B0, N3, minus B0, N1, N2. I need to do this for something I'm going to tell you about. N1, N3, B0, N2 union N3. And for M0, N plus 1, I find it useful to take a Pranoff basis, which isolates a single point, in this case, N plus 1. So if pick M0, N plus 1, has basis psi N plus 1, and then we can take the boundary classes delta 0 S is an N with S has to have at least 2 elements, and we need to have 2 in the complement. So, for example, if we pull the divisor back, that divisor back to M0 N plus 1 along this flag map, the divisor looks like B0 and psi N plus 1 minus the sum B0 S delta 0 S, where S is an N, 2 less than order of S less than the N plus 1. Okay, so this is an F divisor. And in general, any F divisor has this form. We can write any F divisor of this form. And what is the condition? So just to remind you, the way that we're keeping track of them here, we care where the N plus 1 element is. We have a partition, say A1, A2, A3, and then we have the rest, A1 union, A2 union, A3 complement. And it's okay if that complement is empty, we have N plus 1 on the spine. And the intersection, let's say if this is A1, A2, A3, and we can just put the complement down here. The intersection of D with this curve in this form is B0, the union of A1, A2, A3, plus the sum of the B0, AI equals 1 to 3, minus the sum of, just write it out, B0, A1, A2, minus B0, A1, A3, minus B0, A2, A3. And again, you can see this push forward relationship here. Okay. Okay, so that's what we're working with. And so the technical, there's some ancillary divisors that are really important in the proof. And that is, they're defined, so we call them ancillary divisors associated to any divisor D in, and we may as well take it in the F-nef cone of M1 N. and to any subset of the marked points. And this is a divisor just defined by the following. I'll tell you where it lives after I've defined it. So this divisor, this is, sorry, an S. This has, so we take subsets T and S, they're proper subsets, at least two elements. This is this is a divisor on M0 S union N plus 1. For example, let's do a couple of examples. If S is the whole set N, then Dn is just the pullback. Of D. Okay, so if D is an F divisor, this pullback is an F. And so we have, in order to do this, it has to be a divisor here. So a divisor, we need this to have at least 4 elements. So S should have at least 3 elements. So S and N such that the size of S is at least 3. Okay, so let's think of the other extreme. So here's another example. If S has 3 elements, I, J, and K, so we're just in M04. M0 S union N plus 1. This is just isomorphic to P1. Okay, and the Picard group of M04, because it's P1, it's just Z. Okay, so when we look at this D IJK, this just looks like B0 IJK psi N plus 1 minus the set of all B0 XY delta 0 XY, where you take X and Y and IJK. And of course, we're on Picard, we could just replace everything, put it all in one divisor. So if we do that, like for example, XY, and IJK. And let's just pick one of the boundary classes, or we could pick psi N plus 1, like psi 4, doesn't matter. Pick one of the divisors. They're just a point. And this is the intersection of the divisor with an F curve, namely I, J, K. And then this has 1, and the N plus 1 is here, or whatever the other point is. So here it's N plus 1. Sorry, this is just the 1. Sorry, this is empty. Okay, so D is, this is the intersection of the divisor with this F curve, so it's non-negative. If we started with an F divisor, this is non-negative. So in other words, in this extreme case, we have an F divisor. In this extreme case, we have a positive, point. And you always get actually an F divisor. So in all the other cases, so here's a lemma. How many M's do I have there? For S in N, if S has at least 4 elements, and D is an F-nef divisor on M1N, then DS is an F-nef divisor on M0 S union N plus 1. Okay, and we can just very easily see this. So we take the intersection of DS, which I'll just write out. This is B0S psi N plus 1 minus this B0T delta 0T. And we're going to intersect this divisor with a curve here. And this is genus 0. So the only curves we have are like this. So let's say we have I, J, K, and we'll put our N plus 1. This is just the complement And this is just the I, always leave out the zeros, I union J, union K, plus VI, V0 I, plus V0 J, plus V0 K, minus V0 IJ, V0 IK, minus V0 JK. But this is just the intersection of D with the F curve we got by taking that n plus first point, attaching a genus 1 curve with the complement of S here. Okay. So this is just, instead of the complement, this is the complement in, S. So we have the complement in S plus we have S complement. So that's the complement in N. So this is I union J union K complement in this bigger set of F points. So this is an F divisor. And now I can tell you the general principle of the way one uses these ancillary divisors to prove that each of these contraction results hold. So the general principle, and I'll give an example. Is to show that if D contracts a collection of curves, then there is a collection of ancillary divisors such that D minus, or D is the sum of ancillary plus a sum of, this is an effective sum of boundary divisors.
As a clarification question. So
Yeah,
ancillary is associated to every F.
it's associated to two things. You start with your divisor, an F divisor, F-nef, and any subset. So let me,
That's
So-
what is over there.
right, so like, for example, if we have a partition of our set N into two, I can get two ancillary divisors. I have DA and DB. Okay, and now where do these live? So I'm starting with D is an F-nef divisor. And the lemma says that DA is an F-nef divisor on M0 A plus 1, and DB is an F-nef divisor on M0 B plus 1.
It's sort of like a projection of the divisor onto some
Yes,
subset.
yeah,
of the
Right.
basis.
right, and now if we, like, these are actually nef. If D is an F divisor here, and if the F conjecture holds on M1, N minus 1. Okay, now if I take a partition, I want a non-trivial partition, then A and B both have fewer than N sets. So down here, since A is less than N, A plus 1 is less than or equal to N. Okay, now the F conjecture holding on M1N means the F conjecture holds on M0 N minus 1 plus 1. Okay, so these are F divisors on some M0N for, in the range where I know the conjecture is true. So these are actually nef divisors. So DA and DB are nef. Now, let me tell you what exactly. There's, I feel like I dropped a bunch of stuff, but I think it's okay. Okay,
Where is it something nice?
what?
Like, D is on M1N bar and then,
And now I pulled it back. Oh, sorry. I have to pull. Remember, I have to show that that is an F.
pulling the ancillaries back to M0N.
Yes, so for example, let me just do an example like we're talking about now with the two partitions. There are three cases for this two partition. So if you have A unit B is equal to N, and here we're assuming N is at least 4 so that we have, divisors. And so in the first case, let's say that A and B both have at least 3 elements in them, so that those divisors are, on an M05 at least. I mean, sorry, that those divisors are, I want to be in the case that I've covered already. It's either in P1 or it's on an M05. Okay, so then we can write F1N pullback of D as pi A pullback. A is the complement of B, of DB, plus pi B pullback of the complement, plus an effective sum of boundary that depends on those two things. So this is an effective sum of boundary divisors. Oh, that's a composition of point dropping maps.
Okay.
So M0 N plus 1 goes down to M0 A union N plus 1. So I think about this as N union N plus 1. And I can just drop all of the points labeled by B and stabilize if necessary. And then if A only has 1 or 2 elements, I mean, I can take one of them to be smaller, like A, for example, and B is at least 3, then we could write this slightly differently. And then if they're both, so N has to be, N is 4. So the other case is that they both have 2 elements. Because, we can't have them both be 1, right? Right. So then, and 1 and 2 wouldn't give you 4. So we have to take A and B are 2. And then you can just write this as just an effective sum of boundary. Okay, so let me explain now why this is sufficient to prove that these divisors are nef. If you know that the F-conjecture holds for M1 n minus 1. So I've already said that these are actually nef divisors. So if there's a curve that this divisor intersects negatively, well, it's not going to intersect these parts negatively because these are nef. It has to intersect this part negatively. So this part is some effective sum of boundary divisors. And so if the curve is going to intersect one of these effective sums of boundary negatively, it has to be in the support of one of the boundary divisors. So these boundary divisors, the support of the boundary classes, is actually isomorphic on M0N to a product of the moduli spaces. And when you do the intersection of the divisor, you have to pull it back to the boundary, and you do the intersection. You're either going to do it the curve will either occur on, one of these components, and you'll do the intersection there. And now this I is in M0, n+1, and it has to have order, I and I complement have to have at least 2 elements. So the order of I has to be less than or equal to n-1. So the order of I+1 is less than or equal to n. So when you restrict back to these guys, you have the F-conjecture there. So you won't find such a curve when you do that restriction. So if you can write it like this, then that divisor is nef. And that's the idea, okay? So that's the general approach. In this case, that's how it's carried out. For the sibling triplets, so this, if I had 2 of those triplets and they're defined by the same partition, you can use a curve identity like we were talking about before, and I'll just show you quickly what that identity is. So remember, a triplet is just any curve, any single curve that looks like this, labeled by some partition, like for example, I, J, K. So if you have a partition, I, J, K equals N, well, it determines 3 different triplets because there are 3 ways to label, okay? Now, if the divisor contracted 2 of them, so for example, we can just draw any 2. These are siblings because it's the same partition, but just different ways to label, okay? So say you have a divisor that contracts both of these. Well, now I want to use the fact that the sum of these 2 is actually numerically the same as the following sum, where we have I in common plus IJK. So if our divisor intersected those 2, then it has to intersect these 2. I mean, in degree 0. If it contracts these 2, it has to contract these 2. In particular, it has to contract a beloved only child. And because of that result, it's already not. So what this is also telling us about the F-cone or the nef-cone now, because it says that so a single curve defines the biggest possible extremal face of the F-cone, right? And 2 curves define the penultimate size face. And so these 2 sets of curves define faces that coincide. So it tells us that the big faces are touching. And there are other similar curve identities where you take sums of curves, like
In codimension 1, right? So you're saying the big facets are intersecting in codimension.
Yeah. And yes.
So in all the other cases, does the reduction also look like this? No?
No, some of them do and some of them don't. I mean, generally, the other cases can all be proved with a general principle like this. So the general, I call it like the standard procedure, and then I'll give you an example of it. The standard procedure is a little bit simpler than that. For part 3. Is to somehow get that Bn minus Bi is greater than 0. So these should have zeros. B0n, B0i is greater than or equal to 0 for some I and n. You can also make this work. That's the first, that's the most generic case, but it also works if you have B0i minus B0 singleton JK, where the size of the intersection of J and K with I is less than or equal to 1. And then in this case, you can write F1n fullback of D as, sorry, pi I complement fullback of DI plus effective sum of boundary. And in this case, there's a little bit left over. The coefficient, basically, there's a little, if you just have this, and if you know that this is true, then there's a bit of psi n plus 1 here that is not problematic. If you have this is true, what you can do is take, you have some problematic psi n plus 1, you can average it. You can replace it with all classes delta 0 jk union I, and then everything works out just fine. But so let me give you an example of this. There's, I think, just enough time to show you an example. And this example I like because it shows how if a divisor contracts a couple of curves, then it usually leads to more curves being contracted. And so that condition on independence is actually, not trivial. So I thought the example that was doable was like the very last example, where you have that the divisor contracts curves like this for I different than 1, and we'll take n equals 5 just to see. So it's contracting curves C12, 1,2 complement, C13, C14, and C15. Each of these conditions, this tells us something about the coefficients. It says that B012 is B013, is B014, is B015, is 0. Okay, let's see what this tells us. The divisor is an F divisor, so it's going to intersect every curve, F curve, and so this is what's left over is 4 and 5. It non-negatively intersects every F curve. Intersecting this one tells us B0, 1, 2, 3. We've already seen this in one of the cases. B0, 1, 2 minus B0, 1, 3 minus B0, 2, 3 greater than or equal to 0. These ones are 0. So this tells us that B0, 1, 2, 3 is at least B0, 2, 3. On the other hand, we have this curve. And this tells us that this is B0, 2, 3 minus B0, 1, 2, 3. So in fact, these are equal. And the fact that D contracted these two curves tells us that D contracts these two curves. Okay, and we get this information. So we get, for example, that B0, we just proved this is B0, 2, 3, B0, 1, 2, 4 is B0, 2, 4, B0, 1, 3, 4. Each one of these stands for two curves, B0, 3, 4, and B0, 1, 3, 4, 1, 3, 5. But I need 1, 4, 5. So I just killed 1, 2, 3, 4, 5, 10 curves. Okay, these are disjoint. I want to intersect D with 2, 3, 4, 5, and 1. Okay? And when we do that, we get B0, 5. And we get B0, 2, 3 minus B0, 1, 2, 3. I'm putting these in the order that is convenient for me. B0, 4, 5 minus B0, 1, 4, 5. And then we also get minus B0, 2, 3, 4, 5. These are 0. And this is greater than or equal to 0. What I've just shown that B0, 5 minus B0, 2, 3, 4, 5. You can do this in general. I'm just giving an example. And this will tell you that F1, 5 pullback of B is pi 1 pullback of this ancillary divisor, 2, 3, 4, 5, plus an effective sum of that. I know this went too fast, but I just wanted you to see kind of like what happens. You kill some curves, you kill a bunch of curves. And then this is the kind of thing that happens. This is exactly how this is proved. And in this case though, n equals 5 is actually just overlapping with the prior result. Or you can see like let me say it like this. So we kill all of these curves. We're on some part of this nef cone, and this part of the nef cone actually intersects with the part of the nef cone determined by a pair of sibling triplets. Because if you think about the two things that we used, these are sibling triplets. Because you have 2, 3, 1, 4, 5. This is the low numbers thing. 1, 2, 3. Those are a pair of sibling triplets. This is just a function of the n equals 5 situation. But okay. But you can see that the F cone is like connected. And what I'm picturing is like, I don't know, like I picture a soccer ball that's tiled in black and white. And you take any vertex of the soccer ball, and it's either touching a white or a black tile. So if you can show all the white tiles are net, then the whole soccer ball is net. Or if you show all the black tiles are net, then you have all of the soccer balls net. So I wonder if for low n where the conjecture holds, one could like show that you have, you're on the nef cone and you're just like hitting one of these conditions. That would be amazing. But I don't know if I can do that because I'm not such a great graph theorist. But anyway, thank you for listening to my talk.
I missed the soccer ball analogy. Well, there are black tiles and.
Well, I'm just picturing like we could come up with, I don't know, like a truncated dodecahedron or something, but something much more interesting with a lot of different colors. And, maybe all the purple and green tiles represent faces that are nef, and you don't know about the pink one. Like how much, like at some point, like if you could get enough conditions that every one of those faces touches a nef face, then you could be done.
Do you mean like you've had these only children and sibling triplets are the black versus white?
Yeah, or
and then you.
Yeah, it's too simplistic of a picture, but I'm wondering if like really I'm just saying something really basic, which is, it would be great if someone who's really good combinatorially, who could say at least up to some n, where I think the conjecture will hold up to some n, and then it won't hold, and that n might be 12, m0 12. So m0, m1 11. It might hold up to there, or for various reasons. if one could say, okay, you have an F divisor. It contracts and choose two triplets. And it's an extreme, it spans an extremal array of the cone, or just say it spans and, it contracts and choose two triplets. And we've already seen, like, once you contract, one or two curves, you contract a bunch of curves, right? Well, do you run into one of these cones? I mean, one of these conditions?
The best thing can happen is that someone very smart just shows up and maybe for n equals 12, this is like the first case where
Yes,
something happens which is not covered by
Yes.
proposition star
yes.
1, 2, 3.
And it's
8.
gotta be 12, I think it's very likely gonna happen in 12, and then a divisor that contracts and choose two non-related triplets, exactly like you say, and then, okay, now what can we say about this divisor? Let's show it's not that.
I have two questions.
Great.
One is, what do you mean by graph theory? Like, what is graph theory about this? So, second question is, what's a curve that's not F curve?
Oh, that, if you knew that, then you would show that the conjecture is,
So basically, any curve that you can draw as a picture is an F curve.
I mean, what we really need to know are some curves that are not F curves. That would be great.
Nobody knows what not F curves.
I mean, you could define families, one parameter families of curves in MGN, like you could define a, like, a one parameter family of curves. Put some marked points on it. It's parameterized by this space. These are all genus one. I'm picturing cubics. But is that what you mean? Like, what's an example of a curve that's not an F curve?
You just give me an example of a curve that's not.
Yeah, but if you have a curve like this, you can show that it is, a divisor, the intersection of divisor with a curve like this is actually, looks like, is equivalent to, the divisor intersects that, like, it's some sum of curves. Of F curves.
The positive combination of it.
Yes,
Maybe you can degenerate that thing into a sum of F curves.
yeah,
And the question is like, can you do that like all the
yeah, so
That's the conjecture. Every curve, every effect.
I think it would be more likely to find, why am I saying 12? All of the, the best. So Keel and McKernan's proof follows from being able to write an F divisor on M07 as a sum of the canonical divisor and boundary, an effective combination of canonical plus boundary, where the coefficients of the boundary are not too big. And in that case, if you have, they use Mori theory to say that if you have an extremal array that, contracts that negatively, then, something has to happen, and they rule out the, that happening. And so then the question is, like, is every F divisor, can you write every F divisor as an effective sum of canonical plus boundary? And Aaron Pixton showed that there's a nef divisor on M012 that is not of that form. So he used the fabulous Biafley to do it. And he used a combinatorial design to do so. And then you can, of course, parlay that into an example for n bigger than or equal to 12. So then, of course, there are other. So M012 corresponds to M111, and then Matt reminded me that there are interesting things about the cohomology of M111. So that's some fancy numerology there to make you think that maybe there's more going on as the number of mark points gets bigger. And you should expect that, right? That as n grows, that you could define interesting loci. So my guess is that that would be like a smallest case to consider.
M111 was all of odd dimensional homology, something shows to show.
There's some modular form or
Yeah,
something.
there's some special modular form.
Whose result is that? I'll look it up.
I learned it from Hash.
Anyone ever look at the action of the symmetric group on this column? Because you talked about.
Yeah,
symmetry
that's
and
right,
things.
yes.
It seems like that would be sort of.
Yes, so,
You seem to mention that.
right, the SG invariant, part of the F-nef cone of M0 G plus N. You know, that can be related to the F-nef cone of MGN. And the conjectures are equivalent.
But I mean, even in terms of like, you have the whole S of G, S of the NX on MGN, the homology of the MGN, I guess.
Yeah,
So
that's
is that, is that point, like, you're using only like a small part of the symmetric group, like S of G, S of, NX, and G.
You can switch G and N too. Yeah.
But I mean, have people tried to like
Yes.
come up with character formulas and all
Oh,
that stuff?
I don't know. No, probably not. No, but that's that may be something to do. But we've definitely looked at like Gabi Farkas and I have a paper where there's some, like invariant results. We have some results in between.
But it might be interesting if even if there's a part of the cohomology you understood at least, then you could put it into a computer and see like, okay, what are the characters of the representations of SN that are coming out? Is there anything interesting?
Yeah, I think that's a good idea. So anyway, I know it's over. I don't want to keep you here for longer than 2 hours, but so anyway, that's one thing. I think there needs to be a new technique, and I just want to mention my students. So a new technique would involve maybe replacing those, ancillary divisors, which are nef, with different nef divisors. And so what I really do is not this anymore. What I really do is I work on vector bundles on the moduli space of curves that come from representations of vertex operator algebras. And recently, 2 of my students have found nef divisors on M1N from different classes of those VOAs. Avik Chakravarti has found them from parafermion divisors. And Devam Choi, who I mentioned earlier, has used he's taken the dual bundles and taken their term classes with the discrete series Virasoro VOAs. And for a certain class, you actually get a basis for the Picard group consisting of all nef divisors on M1N and a big class of new nef divisors on M1N. So, one possibility would be to get more conditions replacing those ancillary divisors with different nef divisors. And I wish I had spent a little more time on this really good students' results. But anyway, thank you so much.